Today I'll be sharing a joint project designed with one of my subscribers. While it's for a very specific classroom need, many of the concepts presented can be applied to other types of projects. I'll cover the parts used, wiring diagrams, assembly and bench testing, and a little bit of the code, and finally cover the system actually in use in the classroom. Hi, welcome to Resin Chem Tech. Today is a fun little joint project initially requested by a subscriber. Todd, who's a 6th grade computer science teacher, each semester has his student build robot cars that they then race down a track where they are timed. Now, race might be a little bit of a misnomer as these cars really aren't fast, but the faster they are, the more points that they earn. And if they don't make it to the finish, then points are awarded based on where they went off track. Part of Todd's issue is he has to try to help the students film and record the races and run the stopwatch all at the same time. So we reached out wanting to know if we could create some kind of automated timing system with a visible timer that all the students could see. And if we could add LEDs to excite the students, that would just be a bonus. What follows is the system we came up with. Now, you may not be interested in building a robot car racetrack timer, but a lot of the concepts here can be used in many other types of projects. In fact, some of you regular viewers out there may recognize the sensors I'm using from my LED automated stair lighting system. And as you'll see, they're used in a very similar manner. As always, check the video description for a link to a written guide of this project, which contains full parts list and a link to a GitHub repo that will contain all of the code along with a wiki. Let's get started by taking a look at some of the project's general concepts. The goal for the students is to navigate their robot car 10 feet down a 16-inch wide racetrack in the shortest time possible. Now, a single ESP32 will be used to control the entire system. When in auto mode, one time-of-flight distance sensor will detect when a car crosses the start line and automatically start the timer, which is shown on a matrix display with tenths of a second timing. And this was selected over something like a 7-segment display, not only for its size and brightness, but also the better ability to display text or other messages, such as when the system is ready for the next racer. Optional LED strip lighting will also use colors and patterns to indicate when the system is ready, when an active race is occurring, or when a car crosses the finish line, at which point, if using auto mode, the end sensor will also stop the clock showing the final time. A press of the timer reset button will reset the clock and put the system back into ready mode for the next racer, but the timer also includes an auto manual toggle. When in auto mode, the time automatically starts and stops based on the time-of-flight sensor readings. When placed in manual mode, the sensors are ignored and the time is manually started and stopped using a second button on the timer. Now you may be wondering, why am I using distance sensors here instead of something like motion sensors? Looking at something like the AM312 PIR motion detector, we can see that it has a range of up to 3 to 5 meters and a field of view of around 100 degrees. By the way, this diagram is not to scale. Now you can try to narrow that field of view with fins or tubes or tape or paint or whatever you want to try, but regardless of the field of view, there's still an issue of detecting when motion is detected directly in front of the sensor. If someone walks by this area of the track, it will still trip the starting timer. What's more, things like PIR sensors work off of a heat signature, meaning that the robot cars may not even be detected. Even if you switch to something like a millimeter wave detector, you'll still have issues with detecting motion beyond the desired range. With the distance sensor, in this case the time-of-flight VL53LOX, the field of view is already narrower. But what about range in this area beyond the track? Well, since we are measuring distance instead of motion, we can set a maximum distance. We can watch for anything that returns a distance less than the maximum. Any distances greater than this will be ignored, meaning that nothing that passes through the zone beyond the track will trigger the starting timer. We've more or less created a break beam so the timer only starts when something passes within 17 inches of the sensor, practically eliminating false timer starts if someone walks by or around the track area. But you may be wondering about other distance sensors. Here we can see the specs of the VL53LOX versus an HCSR04 ultrasonic sensor and a TF Mini LiDAR sensor. Looking at the ultrasonic sensor, we can see it has a narrower field of view than the time-of-flight sensor, which could be a good thing in this case. But the TF Mini has an even smaller field of view at only 2 degrees. But there are two big issues with the TF Mini. First off, it has a minimum range of nearly 12 inches, meaning the sensor would need to be placed around a foot away from the track. But a bigger issue is the cost. The TF Mini is more than 6 times the cost of the VL53LOX. Why not use an ultrasonic sensor? Well, in my video on the ESP-based parking assistant, I did a real-world test comparing the precision and noisiness of all three sensors. And even at a 1 foot distance, you can see that the ultrasonic HCSR04 is significantly noisier than either the VL53LX or the TF Mini. It gets even worse at longer distances, but for this project, we're looking at distances in the 1 to 2 foot range. If you want to see other ideas of when it might make more sense to use a distance instead of motion sensor, you can check out this video after this one, which goes into more depth about using distance instead of motion for certain circumstances. For me in this particular project, the VL53LOX strikes the right balance between cost and performance. Now you might be able to use the ultrasonic sensor, but I did not test it for this project, and you would need to modify the firmware source code to use the ultrasonic library and functions. While I briefly covered a few of the parts when discussing the overall concept, here are the primary parts that will be used. Now I've already mentioned the ESP32. I'm using a standard 30-pin generic ESP32 Node MCU style board. Now other ESP32s would likely work, including the 38-pin version, which is a little bit more breadboard friendly due to its narrower width, but I'll be mounting my ESP32 onto these pin headers, which will be soldered onto an electro cookie prototype board. This will allow me to complete some wiring underneath the ESP32 and make up for the missing row of holes on one side due to the slightly wider width of this ESP32. I just covered the VL53LOX time of flight distance sensors. What I didn't mention is that these are I2C devices, meaning both could technically be connected to the same two GPIO pins, but each device on the same I2C bus must have a unique address, and by default, each of these have the same address. Now, it would be possible to programmatically change the address on the sensors, but that would require both extra wiring and GPIO pins to connect the X-shut pin, and also would require some additional code. Since the ESP32 has two native I2C buses, we can put each sensor on a different bus and not worry about the duplicate addresses. If you want to know more about I2C and connecting multiple devices to just two GPIO pins, you might want to take a look at this video after this one to see a somewhat extreme example of connecting up to 128 digital devices to just two GPIO pins. Next, I also mentioned the timer display. This is a MAX 7219 matrix display. It's an SPI device and will require 3 GPIO pins in addition to 5 volt power and ground. Unfortunately, in my case, it came with the pin headers pre-attached, and I want my pins to extend straight out the back and not 90 degrees out to the side, so I have to desolder and remove the current pins and solder in my own. Luckily, each 8x8 matrix is just attached by pin headers, so I can easily remove it to access the header pins. Again, I selected this type of display for its size, brightness, and better ability to display text. If you want to know more about adding displays to your project, I have a dedicated video that will cover the MAX 7219 in a bit more detail, along with various other displays and how to set them up in both Arduino and ESP Home. The 3-position toggle and 2 push buttons will be used for selecting the timing mode, resetting the timer, and manually controlling the time when the system is set to manual mode via the toggle. These will be installed on the timer itself. Next is the optional LED lighting. Now, the use of LED strips is optional and can be disabled by setting the number of LEDs to 0 during the initial onboarding process, but I'll be using 2 WS2812B LED strips, one down each side of the track, installed in some aluminum channel with an optional diffuser. The LEDs, I'll also add a logic level shifter to the build, especially since there may be multiple feet of signal wire between the controller and the start of the LED strip. Now, before you jump straight to the comments, I've done numerous other videos on the logic level shifter, and it's been debated ad nauseum in the comments on those videos, including a number of folks stating that this I2C compatible shifter is too slow for LEDs. I've used this same shifter in dozens of LED projects and have never been able to see any visible difference. But ultimately, the decision to include a shifter and the type you use is up to you. I'll just say it's easier to include the shifter up front than it is to try to retrofit it after you've discovered misbehaving or flickering LEDs due to a poor signal. If you find power injection is needed due to the length and number of LEDs, power can be run from the power supply along the strip down the track and wired into the end of your LED strip. If you're not using LEDs, just to omit the shifter and any related wiring and specify 0 LEDs during the initial setup. I'll be powering the entire system using a 5-volt 10-amp power supply. Now, the size of the power supply will be entirely dependent on the number of LEDs used. If omitting the LEDs, you could probably get by with just using something like a 2.5 to 3 amp supply, or maybe even something like a cell phone charger. but do be aware that the Max 7219 display can theoretically draw up to 1 amp of current when fully lit. Now when it's actually running as a timer, the current draw will be significantly less, but it's probably not a good idea to try to power the Max 7219 directly off the 5-volt pin of the ESP32, but instead power it directly off the power supply. We'll see that in just a minute when we look at the wiring diagram. Of course, there'll be various connectors, JST, Wago, Spade. One of the requirements is that this system can be easily disassembled and stored between semesters, so I'll make all the external devices with labeled connectors to make it easy to take apart and put back together again. And finally, I've printed some 3D enclosures for things like the sensor and the timer and the controller, but these are entirely optional and you can substitute project boxes or omit the enclosures altogether. Of course, we'll need wire and soldering iron and all of your other general electronics tools, but these are the primary parts that will be used. And speaking of the wiring diagram, this is the breadboard version. I'll show the final soldered version in a bit, but since the Electro Cookie is really just a solderable breadboard, the wiring will be very similar. I'm showing the breadboard version first because I always start with a breadboard for a proof of concept and some initial bench testing. I'm not going to cover all the details of the wiring diagram here, as you can find a copy of the wiring diagram and some additional wiring details in the written guide to the project, once again linked to down in the video description, but I will make a few comments. First, the project uses a total of 12 GPIO pins, 11 if not counting the LEDs. Naturally, you aren't restricted to these particular GPIO pins, but if you use different pins, you will need to update the firmware source code with different pin numbers. More on the firmware in a bit. You can also see here how I'm powering the Max 7219 and the LED strips in parallel to the controller and not through the controller to avoid drawing too much current through the ESP32. Now, if you're not using LED strips, you might be able to power the system via the USB port on the ESP32, but do recall that the Max 7219 can also draw up to 1 amp, so the safest option is to power the display directly from the primary power supply. But let's try wiring this all up on a breadboard and give it a test. For my proof of concept and my little bit of bench testing here, I've gone ahead and wired up my breadboard version and created a little test track. Now naturally this isn't to scale, but it'll work for initial testing. I've gone ahead and placed the finish line sensor in an enclosure, but the start line sensor is still on a breadboard. I've also gone ahead and thrown the timer in the enclosure, but we'll take a little closer look at that in the final version. Now the goal here is for the timer to automatically start as soon as the car touches the start line here, and for it to automatically stop as soon as the car touches the finish line. For my test car, I'm actually just going to use this little cardboard box, as the students will be building their cars out of cardboard. Now the system is currently ready for the next racer, and the LEDs, while it's probably going to be a little hard to see the LED colors just due to the camera, they're currently yellow for ready mode. I'll turn the lights down a bit so maybe you can at least detect the LED color changes. Let's go ahead and try a simulated race. Now notice my car is back here. It can move around freely behind the start line without tripping the trigger. And as well, people can move around back here behind the sensor and even on the far side of the track, because remember, we're measuring distance here, not motion. So right now I have the motion sensor set at about 12.5 inches. So anything beyond that, anything that moves back here on the other side of the track isn't going to trigger as well. But once the student is ready, they can stage their car. And as soon as they start pulling up and as soon as they hit the start line, notice that the time begins. Now, once that start timer is triggered, you can continue to trigger the start timer and nothing's going to happen. So the student will be able to walk behind the car, since these are wired cars, without worrying about tripping up the start sensor. I'm going to try to keep my arm out of the way here. So they're going to navigate their way down the track for however long it takes them. We'll get down here, and again, notice that as soon as we hit that finish line, that's when the time stops and the race is complete. And again, once that time is complete, we can do anything we want with either one of these sensors without affecting the time. The time stays there so it can be recorded. But once the time is recorded and we're ready for the next racer, we just put it back into ready mode and we're ready for the next racer to begin their race down the track. Now, I previously mentioned a toggle switch on here that allows you to toggle the system between automatic and manual mode. Right now it's in automatic mode, meaning the time starts and stops with the sensors. However, if I reset the time here, and I'm going to flip this over to manual mode, now at this point everything is manual. Notice that the time does not start or stop. Basically the sensors are being ignored. We now use a button on the timer itself to stop the time, which is also reflected on the LED displays. So it more or less turns it into a stopwatch, But part of the reason that I did it this way was if there's some kind of problem with the sensors, or you just don't even want to use the sensors, you can still build the system and use it in a manual method via a timing button, much like you would just a standard stopwatch. And finally, the third or the center position here on the toggle allows you to put the system into standby. What standby really does is turns off the LEDs, turns off the display, ignores the sensors and the buttons. I added this per request for the classroom, where you might want to temporarily turn the system off without powering it down and booting it all the way back up, especially if you've made changes to some of the options. When you're ready to use the system again, simply flip it back to either auto or manual mode, and it is ready for the next race to begin. With the proof of concept and bench testing complete, it's now time to create the final soldered version. Now, in the interest of time, I'm not going to go into the step-by-step process of how I create the soldered version, but you can check out that written guide if you want more information. Here, I'm just going to cover a few key points of the build. First thing I normally do is attach the header pins if I'm using them. As I mentioned earlier, a standard 30-pin ESP32 is just slightly too wide to allow connections on both sides of the mounted board, as you can see here from the header pin locations. I have a row of holes on this side that I can attach to these GPIO pins, but there's nothing over here on this side. So if I were to mount the ESP32 flush to the Electro Cookie board, I would have no way to attach the GPIO pins on this side. But by putting this onto headers, it raises up the ESP32 and allows me to use the connections here underneath the board. And I'm able to make those wiring runs either on the top or underneath on the bottom side of the Electro Cookie board. I've effectively finished all of the point-to-point wiring here on the board, and this will create a 5-volt rail and a 3.3-volt rail coming off the 5-volt and 3.3-volt pins here on the ESP32. I've gone ahead and wired in my logic level shifter for my LEDs, and as you can see, I'm able to complete some of that wiring once again underneath the board. Everything else to be connected is all external wiring for our incoming 5 volts and all of our things like our sensors and timers and our LED strips. Again, I can complete that wiring here on the top, or I can complete the wiring on the bottom, as I've designed my enclosure to allow the wires to come out from the top, bottom, or both. Completed all of the controller wiring. Yes, it looks a little bit crazy at the moment, but every external component's wires are bundled together and labeled, and I'll clean everything up for the final build with some braided cable sleeve and some JST connectors, with a goal of making it all plug and play and easy to disassemble and reassemble as needed. And again, because this ESP32 is mounted on these headers, it gave me a lot of flexibility in terms of completing wiring both on the top and underneath on the bottom of the board. Before we look at the final controller build, let's take a quick look at the buttons, toggle, and the timer enclosure wiring. As I mentioned earlier, the push buttons and the toggle will be part of the timer enclosure. Now, the toggle and both push buttons require a ground connection, but instead of running individual ground connections, we can daisy chain a ground connection and only have a single wire going back to our controller for the ground. The MAX 7219 display will actually lay right on top and rest on those vertical supports on the enclosure, giving us one nice enclosure that will house the buttons, the toggle, and the timer display. This is my final controller build. I've taken those jumbles of wires and I've bundled them up based by connection type. Then I've labeled and color-coded everything, much like the granimals that I fondly remember from my time as a kid. But in addition to labeling and color coding them, I've used different types of JST connectors and also changed the orientation so that things will only connect in a given direction, making it impossible, for example, to connect the clock to the sensor lines or to get something reversed and fry something due to reverse polarity. So again, I've made these cables of a certain length, but if you need longer cables, of course, it would be possible to create something like a JST extension cable that you could add into this if you need to do something like place your timer or your sensors farther away from the controller. And I do still need to put some of this into sleeve. This is the power and the LED data line, but frankly, I ran out of braided sleeve and decided to go ahead and film this instead of waiting on new braided sleeve to arrive. And by using the JST connectors, it allows the system to easily be disassembled and stored in a box when not in use. When it does become time to use the system again, it only takes a matter of a few minutes to pull the components out and snap a few JST connectors together. Okay, let's set everything up and give it all a final test. Okay, here I've set up a full-scale test with 10-foot LED strips spaced 16 inches apart, just like it'll be in the classroom. Now, the only real difference is I don't have the track surface itself, which will be plywood. Now, this is important because it allows the LED strips to be below the surface of the track, and that way these won't act like bumpers to prevent the car from veering off to the left or right of the track. Now, the wiring can still use a little bit of cleanup, but note that even though the system is ready to start timing, I can walk by and around the start sensor without triggering the start of a race. I can walk behind it, I can walk on either side of it, and it doesn't trigger the start. Now, I'm going to use a remote control car that is obviously quite a bit faster than the ones the students are building, so I'm going to attempt to drive slowly. I'll start by slowly moving the car forward, and as soon as it hits the start line, it will trigger the system to start timing. And the LEDs will change to indicate an active race is occurring. Now again, the students will attempt to drive their car down the track without veering off either side of the course. Again, I'm going to try to drive very slowly, but notice that I can now walk behind the car without triggering the start sensor. So I'll work my way down the track, and as soon as I get down here to the very end and touch that finish line, note that the timer stops and the LEDs change to indicate a successfully completed race. And at this point, the system is frozen. I can walk in front of both the start and the finish line timers. But all I've got to simply do is press the reset button on the controller, and it now resets the system for the next racer, and the start line sensor is active. So again, I can come back here, I can place and stage my car anywhere that I want. And as a student, whenever I'm ready, I can simply pull forward and start my race. If a maximum race time is specified, here I have it set to 2 minutes. And if the racer does not reach the end of the finish line within that time frame, then what's going to happen is the system is simply going to time out, turning the LEDs red and indicating that the maximum allocated race time has now been exceeded. So I was just a bit curious to see how fast I could actually drive my car down this 10-foot long track. Well, that wasn't good at all. Okay, so I've reset the track and put everything back where it was. We're going to give this another try. There we go. That was a pretty good run, and I see that I made it in 0.7 of a second. Again, the students' cars won't be near this fast, but it just goes to show that the system will work with timing rapidly moving objects as well as slower moving ones. For those that are interested, I am going to cover just a little bit of the code here. I'm not going to go into a lot of detail because you can find the full source code along with a related wiki in a GitHub repo. Plus, it's still pretty early in terms of the firmware development, and I plan to continue to work on it, so there may be more features available than what I show here by the time you watch this video. If you're not interested in that, feel free to use the links here along the timeline to jump ahead to see the actual use of the system in the classroom. The firmware for the ESP32 is written in C++ using the Arduino IDE. Now, do note that only a single source code file is needed, but that a special no Wi-Fi version is currently available, but likely will not be supported in future releases. The no Wi-Fi version does not contain any sort of web interface or other ways to change the settings or options other than editing the source code, compiling and uploading via USB, since over-the-air updates are also not available. However, if you need to use the non-Wi-Fi version but have never used the Arduino IDE and don't know the first thing about C++, yet need to make small edits to things like the sensor distances or maybe the number of LEDs, I do have another video that covers the step-by-step process of installing and setting up the Arduino IDE to work with ESP boards, including examples of making minor changes like required here for those that are unfamiliar with C++ or the Arduino IDE. But it is strongly recommended that the full version be used if at all possible, as this will allow you to onboard the system to your Wi-Fi while specifying some settings up front. Changes to some of the other settings, and more are expected in future releases, are also possible via a web interface without requiring modification of the source code. The Wi-Fi enabled version also includes the ability to upload new firmware releases wirelessly over the air. The source code is well documented, and full instructions on installation, setup, and use of the system will be available in a wiki by the time this video is released. But now the most important part. Let's see how the system actually worked out in the classroom. The day prior to use, Todd and I set up and tested the system in the classroom using one of the actual cars. Now note that due to simple time constraints, there isn't a plywood track, so tape was used as the out-of-bounds markers. But the LEDs didn't always stop the cars from jumping the track anyway. The good news is that the system seemed to function without any issues. So the system was put through full testing the next day, which was the last chance for students to practice and tweak their cars. While the system functioned fine, there were a few suggestions for some improvements. So Todd would sit here behind this desk during the actual race so he could monitor the cars and also record the final times. But with the current setup, he couldn't see the final time, and bending down to reset the system between races was inconvenient. Asking the student racer to reset the time after the race led to other issues, such as inadvertently bumping and misaligning the end sensor. So he asked if the web application could show the final race time after each race and also provide a button to reset the system back to ready mode. So I was able to make some quick changes to the firmware that I would flash to a new ESP32 that I would bring over and swap out the next morning. But this brought up another problem. Obviously, the controller needs to be on Wi-Fi to be able to access a web interface. And since the school provided an open guest network, it was no problem getting it on Wi-Fi during the onboarding process. But after that, you need to get the IP address. Normally at home, you would use your router to determine the IP address that was assigned, but that wasn't possible at the school. Instead, we had to file a ticket with the IT department and wait to hear back from them in terms of what the assigned IP address would be. There might not be time to do this the morning of the actual races itself, so I made another small change that actually displays the assigned IP address on the timer during the boot process. This worked out great, and we were able to swap the controllers with no issue and without any IT involvement. Luckily, I was allowed to attend the actual races, which was a lot of fun for me. Now, some groups struggled just a bit out of the gate, but each group was allowed 2 runs with a 5-minute pit stop to make adjustments between runs. Others would almost make it to the end before veering off course, but a number of groups were able to successfully navigate to the finish line. As you can see here, even though the end sensor was slightly misaligned, causing a slightly early trigger, all students were racing under the same setup, so it removed any human error when using something like a handheld stopwatch or other manual timing method. If you want to see more of the actual races, Todd shares all of his recordings of his races on his YouTube channel, and you can find a link to that in the video description once he posts his video. I'd like to thank the 6th grade class, the principal, and the other staff at Kitley Intermediate School for allowing me to be part of this project. And a special thanks to their teacher, Mr. Todd Norcross, both for the idea and working so closely together with me to make it happen. I rarely do outside projects like this, but I couldn't pass up this opportunity for both an interesting project and maybe helping out just a little bit to inspire younger kids towards STEAM topics. I'll be back soon with more videos on DIY electronics, LEDs, and home automation, including another joint project I'm currently working on that I hope will be completed sometime this spring. But until that time, I'd like to say thank you for watching, and I hope to see you soon.